Okay, so the last time we were doing petroleum production engineering, we spoke about what petroleum was, the origin of petroleum, source rocks, what a reservoir was. We spoke about migration, the two types of migration. We spoke about porosity, we spoke about compressibility, we spoke about permeability. Those are the properties of the reservoir. So we'll continue with other properties today. The other thing we'll be looking at today is called saturation. We're not talking about saturation, we're talking about the fact that the pores in the reservoir or the reservoir rock are being filled with a certain fluid. In this case, the fluid can be water, oil, or gas. In the case where we have water, we are going to use the subscript W. For oil, we use O, and for gas, we use G. Right? So we are saying that the volume of the pores is being filled with a fluid, which could be water, oil, or gas. This is when we are told that we have a saturated reservoir. So we need to pay very close attention to the kind of questions we are given. So if we are told that we have a saturated reservoir, then we are going to work with the assumption that the pores are being filled with a fluid, which could be water, oil, or gas. Now, sometimes the question can be specific and tell you that it's filled with maybe just one fluid. So it might be saturated with just water. In that case, oil and gas will go to zero. Or you might be told that the reservoir is saturated with just maybe oil and water. So it means that the volume of pores being occupied by gas is zero. So these are just a few things to note. Now, when we're looking at the saturation, it's going to be a fraction. So it's going to be the volume of oil, water, or gas, right? That is occupying the pores divided by the total pore volume. So if you're looking for the saturation of oil, we have S subscript O. It's going to be the volume of the pores occupied by oil divided by the total pore volume. If we have the saturation of water, it will be S subscript W. We'll have the volume of the pores occupied by water divided by the total pore volume. And if it's gas, so it was supposed to be G instead of I. So we'll have the saturation of gas, it will be the volume of the pores occupied by gas. So that's supposed to be G divided by the total pore volume. And since they are all fractions, when we sum all of them up, it should give us 1. Once again, in the case where maybe we are told that it's just water and oil saturating the reservoir, it means that there wouldn't be any saturation of gas. So that side goes to 0. So we just have SW and SO being summed up to give us 1. Okay. So we'll take an example relating the porosity and saturation, right? So here we are told that we want to calculate the porosity of the sample below. We've been given a dry mass sample, which is 95 grams. We've been given the mass of the water saturated sample, which is 115 grams. We have the density of water, and we have the mass of the saturated sample immersed in water. So we'll see what they're talking about here. But before we even get into that, we are being told to find the porosity of the sample. And remember that we said that the porosity, right, was equal to the volume of the pores divided by the total volume of the sample. So it means that to be able to solve this question, we need to find the volume of the pores and then the total volume of the sample. And all this data is going to help us with that. So the mass of the dry sample that was given to us was 95 grams. The mass of the water saturated sample was 115 grams. What we can do is that if we have our dry sample this way and we have our saturated sample this way, so the black spaces will be representing the pores, and when they are filled with fluid now, they are blue. So that's what we are representing them with, the pores being filled with water, because the saturation is with water. Now, if it's a dry sample, it will come with its own mass, but the moment it's saturated with water, what's going to happen is that the water is also going to come with its mass. So the mass of this sample here is going to change, right? It's going to be the original mass of the dry sample plus the mass of water saturating the pores. So if we should find the difference between the two of them, right, what we are going to have is that the difference between the mass of the saturated sample and the mass of the dry sample is going to give us the mass of the water that was just occupying the pores. The reason why we need this is because we said earlier that we need to find the volume of the pores. So this was going to help us find the volume of the pores. The mass of water occupying the pores, right, is what we can find if we find the difference between the mass of the saturated sample and then the mass of the dry sample. And we can actually relate it to what we have over here. So here we are seeing that the mass of the saturated sample is equal to the mass of the dry sample plus the mass of water that is actually doing the saturation. So in effect, we can also say that MC is equal to MB minus MA, which is the same as what we are saying here. MC is the mass of water occupying the pores. MB is the mass of the saturated sample, and then MA is the mass of the dry sample, right? So to find the mass of just the water that did the saturation, we'll take the mass of the entire saturated sample minus the mass of the dry sample. Now, before we come to this diagram, we'll use this diagram later on. So before we come to this diagram, we said that our density is mass over volume, right? And in that effect, volume is mass over density. The mass of the water that saturated the sample is given by this. Remember, we did MC is equal to MB minus MA. So that's the mass of the saturated sample minus the mass of the dry sample. That's what we've used here. So the mass of the saturated sample was 115 grams, as we see here. The mass of the dry sample was 95. So when we find the difference, they're having 20 grams. Now we can find the volume. This is the mass of the water that saturated the sample. So we can find the volume of the water that saturated the sample. So we know that the volume is equal to mass over density. The mass was given as 20 grams. Density as 1 gram per cm cube. So when we do this, we are going to end up with 20 cm cube. Right. So this is the volume of water saturating the sample. But the volume of water that saturated the sample occupied the pores. So that's going to be equal to the pore volume. So it means that our pore volume is also going to be 20 cm cube, and that's the Vp. So we found the first part of our equation where we need to find Vp over Vt. We found the first part of our equation. Now the next thing we need to do is to find the Vt. That's where this diagram would now help us. So we had the saturated sample and we immersed the saturated sample in water. When we do this, what's going to happen is that the weight of the sample, the actual weight of the sample, will be acting downwards. But the water is going to offer some kind of opposition to it. So this is all based on Archimedes' principle and all those things we did with when we're studying density. So the water is going to have some kind of opposing force to the actual weight of the sample. That's going to be the upthrust. So the weight we would actually end up measuring, that's the apparent weight, is going to be equal to the actual weight minus the upthrust, right? So that's what we are going to have. So once again, we have the saturated sample immersed in water. When that happens, the actual weight of the sample will be acting downwards, but it's going to be opposed by the upward force in the water. That's the upthrust. So the difference between the two give us the apparent weight, what we can actually measure. So the weight we'll measure is not going to be the actual weight of the saturated sample, it's going to be its apparent weight. So we see that over here, the apparent weight is equal to the actual weight minus the upthrust. In that effect, we can see that the upthrust is equal to the actual weight minus the apparent weight. The reason why we are finding the upthrust is because the upthrust is going to be equal to the mass of water that is being displaced. So that's the mass of water displaced. And that's what we have over here, right? So they found the upthrust. So we had the actual weight of the saturated sample, which we were told from the question was 115 grams. That's the mass of the saturated sample. Then we have the mass of saturated sample when it was immersed in water. That's the 60 grams. So when we find the difference between the two, we'll have the upthrust. So that's what we have over here. The difference between the two values to give us the upthrust. Now we said the upthrust is going to be equal to the mass of water displaced. That's what we have down here. So with the same thing we did earlier, you know the volume is mass over density. And the mass in this case is equal to the upthrust. So we have the upthrust over the density. So you are going to have 55 grams divided by 1 gram per cm cube. And that's going to give us 55 cm cube. One thing to note is that so normally the weight should have been given in Newton. But we'll be giving the weight in grams. When it's given to us in grams, you can just go ahead and do this. But in the event where maybe we had it in Newton, right, we would have to divide the answer. This would have been, after that value would have been in Newton. So maybe we would have had something like 550 Newton. And would have divided it by 10 meters per second squared, right? So that would have been the weight divided by the acceleration due to gravity to get the mass. But that wouldn't be the focus for this one because we're given everything in masses. So we can just go ahead to use the actual masses when we are working with the upthrust and the weight. Okay, so that's just by the way, just something that I wanted to put across. So as we're seeing, the volume, the mass of the water that was displaced, we said was equal to the upthrust, so that was 55 grams. And we can find the volume of water displaced, so that's going to be the mass divided by the density to give us 55 cm cube. Now, the volume of water displaced, remember when you immerse a block in water, the volume of water that gets displaced is equal to the total volume of that block. Even if the block is porous, it's going to be equal to the total volume of that block. So the volume of water displaced is going to be equal to the total volume. So that's going to be equal to our Vt. So now we have our Vp and we have our Vt. right? So we have the volume of our pores, we have our total volume. We can use this to find our porosity. So we have the, oh, this was supposed to be the other way around. It's supposed to be VP over VT. Sorry for the mix up. So we had the volume of our pores to be 20 cm cube, and that's of our total volume to be 55. So when we divide the two, it gives us the porosity. And the question is asking whether this is the effective or the total porosity. So if we think about it, we had our dry sample. So we had our dry sample, right? And when we saturated it, it was now filled with fluid. So the porosity we calculated was the porosity of the sample, or the porosity based on the pores that were filled with fluid. For that to happen, it means that fluid should have found a way to get into those pores, right? It's possible that there could have been residual pores that wouldn't be filled. So it means that the porosity we are calculating is going to be for the pores that were filled. In the case where there were residual pores that couldn't be filled, then it means that we are going to have the effective porosity. We can't have the total porosity because those pores will not be filled. We can't calculate the porosity based on those ones as well, right? So for this question, the best option we can go for is the effective porosity because we are calculating the porosity based on pores that were filled with fluid. And remember we said that for effective porosity, we are looking at pores that are interconnected or connected to other formations such that fluid can flow into them and out of them. So the fact that fluid managed to flow into those pores means that we are dealing with effective porosity. Okay. Another thing that we would be looking at is what we call the original oil in place. Now, we said that porosity was equal to the volume of the pores divided by the total volume of the sample. When we are dealing with the reservoir, we can see that the volume of the reservoir is equal to its area times the height, right? To give us the total volume of the reservoir. So I can replace the VT in equation 1 with the AH here. Or I can just make the VP, the volume of the pores, the subject. So that's what we've done over here in equation 3. We made VP subject in equation 1 so that we'll have the porosity times VT. And from equation 2, we said that the VT was A times H, so this was equal to VP. So if the VT is equal to A times H, then we have porosity times A times H to be equal to our VP. So that's what we have for equation 3, right? Now, beyond this, we said that the saturation was equal to the volume, that's the saturation of oil, it's equal to the volume occupied by oil divided by the total pore volume, right? So it means that I can make the VO subject here to have equation 5. Is that fine? So it means that from equation 4, my VO is equal to my SO times my VP. But I have the VP from here, so it means that it's going to be SO phi then A times H. So this is actually what we are going to be working with equation 5. But the thing is that with reservoir, when we are dealing with reservoir, the kind of units we have would require that we have a certain conversion factor so that we can get an answer if we need it in barrels or a meter cube. So the question might ask you to find the original oil in place, and your units might be required in barrels or a meter cube. So the original oil in place, are looking at the oil that is in the reservoir, like saturated in the reservoir before you started doing production. That's what they're talking about, original oil in place. It's also possible to have just oil in place. So you're not looking at the original, right? Yeah, so the difference between the two of them is that for the original, you're looking at the just before production happened. So you're looking at the initial oil in place, like before anything at all happened. So the saturation of oil in that case would be the initial saturation. So you use, sometimes you see this notation. So it's the initial saturation of oil. Things that when you start producing the oil, the saturation can change. So if it's just supposed to be oil in place, then they can just use the saturation of oil just like that. But here we are just going to take it that our SO here is the SO over here is going to be the initial saturation. Okay, because we just want to, we are assuming everything here is under the initial conditions. We've not started producing. Okay, so the conversion factors we work with, there's a point where we use 7758 and there are points where we use other things. So we'll come to that in the next slide. But the equation for oil in place at the end of the day becomes this. So it's a conversion factor times what we spoke about earlier. So we have our AH porosity and then our saturation of oil, right? Now there are times that we might be asked to find the standard volume of oil. When we're dealing with the standard volume of oil, then it means that we have to bring in a different relation. So we can use the oil formation volume factor. The oil formation volume factor here is BO. and that is equal to the volume of oil at reservoir conditions divided by the volume of oil at standard conditions. If we should divide everything by the um, total pore volume, so maybe I have the volume of oil at the reservoir conditions. Let me make that one VA, and then the volume at standard conditions, maybe VB. But let's say it's still in the rock. If I divide VA over VP and then VB over VP, what I'm going to get for this one here is going to be the saturation of the oil at the reservoir. And what I'll have here is going to be the saturation of oil, this under the reservoir condition, but this is going to be the saturation of oil assuming the standard conditions, right? So all we are doing here is that now the SO here, if we want it at the standard volume, or let me do it this way. So if I want the standard conditions, what I have down here as the denominator, right? It means that my DO can be likened to SO over the SSC. So if I want the SSC, it has to be the SO over the BO. So it means that instead of me working with the saturation of oil in the reservoir, that under the reservoir conditions, I'll have to use this now to get it under the standard conditions. That's why we are now dividing it by the oil formation volume factor, right? Now, there are also cases where we might assume that the saturation is um, just based on oil and water. So we can say that SO plus SW is equal to 1. In that case, SO is equal to 1 minus SW. So the reason why I'm doing all of this is because we've seen formulas that are in both this form and this form, where you might be given the saturation of water under reservoir conditions and the saturation of oil under reservoir conditions. It might be asked to find the original oil. So it might be asked to find the oil under the standard condition, the standard volume of oil. So when it's the standard, then you now have to divide it by the BO, right? And we can assume that the saturation is just between oil and water, right? So we are not dealing with gas. That's when we want to work with oil in place. We can assume that there is no gas unless the question states that maybe there's gas involved. Then we would include the gas in the saturation. So we might have the SG coming in here. Then we might have the minus SG. That's if the question said that we should include the saturation of gas. So the main equation that we work with is equation 6. This is the one that we actually use. And yes, this is the format 7758 times AH porosity times SO. These other equations are just for you to have in mind in case you come across something that's asking for the standard volume. Okay, so the area for the formula that we are using here, the reason why we are using this conversion factor of 7758 is because the area that we are working with for that formula is in acres. The thickness or the height, the H, is in feet. The porosity is a fraction. We don't want it in a percentage form. So if we're told that the porosity was 22%, we would use 0.22. Right? So that's what we use for the porosity. The saturation is also a fraction. The BO is the oil formation volume factor, so it's also a fraction. So we are saying that the 7758 here is a factor that will convert the acre and feet aspects that we are having from the A and H, right, into barrels. The A and H part of the formula, it will give us a unit of so this was the A and H part of the formula. It will give us a unit in acre feet. But we want this in barrels, so we multiply everything by 775. That's the conversion factor, right? So that's why we do that. So if the question had given you maybe the area in a different unit, maybe it gave you the area in even if it gave you the area in feet or gave the area in meter, sorry, feet squared or meter squared, because you might want to use this conversion factor, you might have to change it to acres first. So you need to know the conversions. Now there are other conversion factors that we can work with. So sometimes we might be asked to find it in feet cube, the volume, the volume of the oil, the original oil in place in feet cube. So instead of the 7758, we can use 43560 to get an answer in feet cube. Or we can use a conversion that 1 barrel is equal to 5.615 feet cube. So we can find the answer using the formula for the barrel. That was the 7758 phi SO, right? And then we can multiply this by 5.615 to get an answer in feet cube. Here, answer in feet cube, right? And even beyond the something we have to find the answer in meter cube. So for this one, too, we can decide to just multiply the answer in barrels by 0.159 to get an answer in meter cube. So we'll have AH phi SO times 0.159 so that we have our answer in meter cube. So you just need to know the conversion factors. But if you are going to use this formula, it means that whatever area they give you, if it's not in acres, you have to change it to acres. And whatever thickness or height they give you, if it's not in feet, you have to change it to feet. So we have a very simple example here. If you're given a formation that is 3 meters thick, so that's our H. And we've been told that the volume of the oil, we want to find the volume of the oil in place, and the area we've been given is 60 acres. So that's what we have here. So we're told to report the volume in cubic meters and then in barrels. We've been given the porosity of the core, we've been given the oil saturation, the water saturation. So we can see from this that the oil saturation and water saturation, if we add them up, the 0.49 and 0.51, it will give us 1. So it means the saturation is just based on oil and water. So in the case where we're told to find the standard, we can use SO over BO, or you can use 1 minus SW over the BO, and they'll both be fine. So for this question, it's just straightforward. We just end up using the formula, the 7758 times the A, the H, the porosity, and the saturation of the oil. So we have all those parameters that we just put it inside to get the answer in barrel. But the question also asks for the answer in meter cube. So we can multiply it by the conversion, the 0.159, so we can have our answer in meter cube. So that will be it for now.